Hello, calculus students. Nice to see you again. So we're continuing on with chapter 8 and 812, talking about cylindrical disks, which I got to a little bit in the last video. But before we get into that, let's recap what we did in the last video or recall. So in the last video, what happened is we took the cross section of, say, and I'll just do the example problem we did. Well, no, I'll do an orange. I did an orange and I did it myself in the video. And the big thing is when we take cross sections of orange, what does it create? Well, it creates cylinders, or at least like cylinder shapes, where if you have an orange that's very spherical, doesn't necessarily have to be spherical, but it was here. Well, when we took cross sections of it, cutting it along the way, what happened was we get, if I pull out this one, you get the idea of cylinders, okay? And then the idea of calculating the volume is we calculate the volume by adding, the volume of each cross section, which the volume of a cylinder is pi r squared h, again, because pi r squared is the area of the base, h because there's h many of them, and they'll fill up the space. Now, where are we heading? So that's the idea of filling up volume. Now, we're going to apply this a little bit more to the math standpoint in this video. So example 1. Let's say we have the function f of x is equal to x cubed. And I am going to look at on the domain just where x is greater than 0 here. Okay. So if I make a sketch of this. So x cubed again would look something like this. But I'm only looking when x is greater than 0, so I'm only going to highlight that part where this is meant to be dashed just to make sure you remember that. Okay. Now, if we wanted to find area under the curve, how would you find area under the curve? So for just area under the curve, remember that we would use rectangles where it comes from rectangles. I'm going to evaluate it. I'm going to say that's 2, but we'd make a rectangle. And then we more or less the integral for area under the curve, we do an integral, and that adds up, all the rectangles underneath. Adds up all the rectangles of an infinitesimally, small width. Or they're very small widths that would more or less make it in what we call an exact area. All right? So if I pull this rectangle out from area under the curve, if I pull this out right here, what are the dimensions of this rectangle? Now, remember, it's an infinitely small width. So the width of these rectangles were dx, that very small change in x, right? It's not 0. It still has a width. It's just very, very tiny. And then the height of this rectangle, well, the height just goes up to what the curve is, where the curve is f of x, which is x cubed. So you could call the height of this cubed f of x, or, x cubed, since they equal each other, right? But that's your height, and that's your thickness, okay? Now, let's say we rotate this curve about the x-axis, right? And I like to draw my arrow this way to imagine it coming towards you, like off the paper, towards you, and then underneath the paper, and so forth. So let's say we rotate it. What would we get? So if we rotate this, I will do it, add a color to it. How about that? So if we rotate it, what would happen is that this curve, I know it's happening here, but this rectangle is going to come around. It's going to go back around into what is a cylinder, and it might be very hard to see, right? If you wanted to, here is a book I have to help you kind of see this and see if I can do it from the webcam's perspective here. So you're finding the area under the curve. Say, let me do it on paper. Take up this paper really quick to help you visualize this as best I can in this setting. All right. So that's the picture I did. And I know you can't see it that I have on my paper over here. All right. So say I have a book that's like this, okay? And that book is going to represent the rectangle. All right, I'm going to do it this way. Well, yeah, that's one of the books. All right. Now the idea is, say you were looking at it from a sideways perspective. So say you're looking at it this way. You're looking almost, so we're going to turn our head. Let me visualize this from the webcam. Instead, pretend your eyes are on this side looking at it. All right. Was that right? Yeah. Now, if it rotates towards you, notice what happens is if you rotate this rectangle, and this down here would be the x-axis right here, or if you rotate, well, no, the x-axis, where am I at? This is the curve. Let me make sure I have this right. And we're rotating towards you. Yeah, like this is what I meant by this picture until you make back to where you are. So if you can see it from the side view, if you're looking at it through this way, notice that when it rotates, what do you end up creating? And I don't even know if you can follow what I'm doing, but if you're mapping this corner of the book, and you rotate, notice that you end up creating a circle, right? So what ends up happening, and that it's hard to visualize in this setting, is that this right here, maybe I draw it out here, is you create a circle. Well, mine's backwards now even. And it has a width, of course, because there's a width of the book, right? So this right here was the x-axis. That. So if you imagine, there was my rectangle, it was in this section, and it was rotated in a way that creates this cylinder, right? So what's the volume of this one cylinder? The volume of this one cylinder, this cylinder, well, remember, volume is pi r squared h. That's the generic formula. Now, what's the radius of this circle? Well, notice that the radius of this circle is just the height. Where's my green pen? There it is. The radius of the circle is just the height of the square. So the radius is f of x, or again, that's x cubed. Now, what's the thickness of this cylinder? The thickness, remember that book, is dx. Now, again, it's because it would be infinitely tiny small. We'd be cutting these up where we would make a lot of these. So that's the thickness, or, in the formula itself, we're going to be referring to it as the height. So what's the volume of this one cylinder when rotated about the x-axis? Well, it's going to be pi. The radius then would be f of x squared, so the radius is being squared, times the height, dx. And I don't have to put f of x here, right? I could definitely put this as x cubed squared dx, because that's the height of the rectangle. All right. Now, I might be confused with height and height. All right. So that's why maybe we don't use height here and we just talk about thickness. So I don't confuse you with the height of that rectangle being the radius. Now, that's great. And that helps us find the volume of this one cylinder. But say I wanted to find the volume from 0 to 2. Okay. So say at 2, we cut this off, and we end up creating a shape here that would look something like this. What's the volume of that shape? Okay. Now, we notice that we found the volume of one cylinder that's within there. And if we cut this up infinitely many times, how do we add up all the volumes? Well, we need to add up each volume, or each volume of each cylinder of infinitesimally, I spelled that wrong, tiny widths. Same thing we did with the orange, right? The idea is that we're going to cut it up, and if we cut it up very small and so many of them, it'll make up an exact volume. All right. So to get the exact volume here, how do you add up all of them? Is we're going to add them up. And that is the integral, or again, a summation. So we have to add up the volume, and we're going from 0 to 2 of each cylinder. So what is the volume of each cylinder? Well, we did that over there. So we're going to get the volume is going to equal the integral from 0 to 2 of pi times the radius of every cylinder, which is x cubed squared, times the thickness or the height of every cylinder, which is dx. And that right there will give us the exact volume of this shape, right? So again, this right there is your radius, and this right there is your height, fulfilling the formula volume equals pi r squared h of a cylinder. Okay, so that's the volume of a cylinder. The integral sign makes it so we add up infinitely many cylinders with tiny widths. So let's calculate this out and see what we get. So what we're going to get here is, now I'm going to pull the pi in front because it's just a constant. So maybe write this as pi from 0 to 2. That'll become x to the 6th dx. Then we'll have, and I don't want to move the screen yet, so then it'll become pi, taking the antiderivative x to 6 would be x to the 7th over 7. And we're evaluating from 0 to 2. And then what we end up getting here is pi times 2 to the 7th over 7 minus 0 to the 7th over 7, which ends up being, if I don't even simplify this, you're going to get 2 to the 7th pi over 7. And it is volume, so it's going to be units cubed. And there is the exact volume of that space. Okay. And that's the idea. So we're taking the idea of a rectangle that would be used to find area of a curve, where those rectangles, where the function itself always represents the height, and then the thickness is dx, that infinitesimally small change in x, because again, d just stands for delta anyway. And then when we rotate it about, we end up creating a cylinder where the radius of that cylinder, because again, we use the formula pi r squared h, the radius of that cylinder is just the rectangle itself, the height of the rectangle. And then the thickness is dx of that rectangle. That's the thickness of the cylinder. Let's look at a few more examples to help you visualize this. And again, I might not be the best drawer yet. I'm still working on my drawings. Believe it or not, this has come a far way for me. I was not even this good a long time ago. So I'm still working on it. I'm getting better. Let's look at a second example. Example 2. Let's do, wrote it down. Let's do the volume of the region bounded by y equals root x, x equals 5, and y equals 0. And we're going to rotate about the x-axis. Okay. So let's do this one. So we'll sketch this first, as always. Okay. So root x is going to look roughly like that. There's your y equals root x. X equals 5. 1, 2, 3. Well, just draw it like so. There's x equals 5. And y equals 0, which is here. So there's the region right here. And we're going to rotate about the x-axis. Okay. So if we were to look at a cross section of this, do it in color to help you see it, hopefully. And we rotate it about, we're going to end up creating that cross section that's a cylinder. Now the radius of that cross section, your radius is going to be the function itself, which is root x. And then the thickness of that cross section is dx. Okay. So to calculate the volume of this region, we just need to fill the space up with infinitely many of these. We'll use the integral. It'll sum up. And we're going from 0 to 5 of the volume of every cylinder that fills in this space. So that's going to be pi radius squared times the height, which is dx. And again, that comes from your formula of a cylinder, pi pi r squared h. Okay. Going through the math now, it would be, pull the pi out in front. It would be pi 0 to 5, root x squared is just x dx. This will become pi times x squared over 2 from 0 to 5, which is going to equal pi times 25 over 2 minus 0 over 2, which gives us 25 pi over 2 units cubed, is the volume of this region bounded by the x-axis, which, what does that create here? Is it looks like it creates a bowl almost, like so. That's what we found. Good. And we'll do one more example. Example 3. Let's do the volume. And again, if you need to pause the video, I hope you know that by now. Bounded by y equals x squared, y equals 6, and x equals 0. And we're actually going to do this about the y-axis. Okay. So let's make a sketch of this situation. So we have y equals x squared, and I'm just going to sketch this part of the graph. And I'll explain why in a second. Y equals 6, so at some point 6 up here. And x equals 0, which is this line here. That's why I didn't draw the whole parabola, because I don't need this side. So that's the region we're looking at that's bounded by those. And we're rotating about the y-axis. So imagine it rotating this way. So it's going to come out of the picture towards you. So in this one, yeah, we're going to end up creating something like this here. So let's look at a cross section. So in this case, the cross section, since we're rotating about the y-axis, your rectangles are going to be drawn horizontally. Right? So let's pull that rectangle out and study it. Well, not the rectangle itself. We rotate about it, we're going to get a cylinder that looks like so. Again, if you were to rotate this about, you end up getting a cylinder. I might have messed up that picture because that wasn't parallel. Oops. Hopefully you're still with me. All right. What's the radius of this cylinder? Your radius, well, it's just the function, the distance from 0 to the function. But since we're in other words, the thickness, let's talk about the thickness. How thick is these? Well, we're going to cut these up along the y-axis here. So as we cut them up, what's the width of every one of these? Where they're going to be that very small change in y. So our radius, being our thickness is in y, will also be in terms of y. So if we look at our radius, y equals x squared, and we solve for this in terms of y, we'll get x equals root y. So our radius here is root y. Okay. So again, that's just the function in terms of y. So now to evaluate the volume of this curve, it's going to be the volume from 0 to 6. And the volume of every cylinder is going to be pi times the radius squared times the height, dy. Okay. And this one is going to work out much like the last one. Maybe I should change it up to help you see the math, but that's okay. We'll keep with this problem. So it'll be pi root y squared will just be y dy, and we'll just calculate this out. We end up getting pi, the antiderivative there would be y squared over 2 from 0 to 6, which would give us pi. Plugging that in, you'd get 36 over 2 minus 0 over 2, which implies to 18 pi units cubed. And there you go. Now, it's important you know how to do this by hand, but it's also important that you know that you can use a graphing calculator to check your answers. So say you wanted to check this, we would have here math integral, and I'm always going to pull my pi out. That way I don't mess up with the parentheses there. So it's going to be pi, and you don't have to. I guess it honestly doesn't matter. 0 to 6, and then your radius squared, which ended up just becoming y, dy, and we get 56 in that number. Now we got 18 pi. Hopefully that gives us the same thing, and it does. So we are good. Okay. So there's volume and how it works with math. The idea of building your cross sections are cylinders, and we use integrals to add up those infinitely many cylinders of that infinitesimally small widths. Hope that helps. I hope you're doing okay with the visualizations. That's always the hardest piece of this. And if you have questions, draw them out and try to visualize best you can. Okay. I am available in office hours if you ever want to come chat or ask me any questions. All right. Bye-bye.